Hello, and welcome to The Complete History of Science. Series 7, Episode 7, The New Astronomy. The year 1602 was a watershed for Johannes Kepler. Up to that point, much of his life had been a great struggle. He was born poor to an absent father and a difficult mother. As a child, he entered a Lutheran seminary, which saved him from a life of destitution. But growing up in the church, he experienced many cold, friendless years. For a while, he found his place as a mathematics teacher in Graz, until the Counter-Reformation forced him into exile. Fleeing to Prague, his only possessions were what he could carry on a small cart. So, it was a remarkable turn of fate when Kepler was made imperial mathematician by the Holy Roman Emperor Rudolf II. Rudolf was a great patron who had assembled in Prague some of the finest artists and scholars in Europe. At court, painters, poets and sculptors mixed with astronomers, alchemists and natural philosophers. Kepler, as the new imperial mathematician, was thrust into the heart of this busy intellectual world. He relished the opportunity, acquiring a busy social life and making many close friends. In July, he moved into a new home, along with his wife Barbara and stepdaughter Regina. Barbara soon gave birth to a daughter, Susanna, their third child and the first to survive infancy. Just as his personal life was looking up, Kepler was also entering the most productive period of his working life. He had inherited his position from the great Tycho Brahe, and the emperor expected Kepler to continue Tycho's work. All of Tycho's astronomical instruments were placed in Kepler's charge. He was also given responsibility for Tycho's unpublished manuscripts and production of the new set of astronomical tables. To this end, Kepler was also handed all of Tycho's observations. These, not the quadrants, were the real treasure. The quantity of data was enormous. It included thousands of accurate measurements of the sun, moon and planets, taken over a period of 30 years. The amount of material was so overwhelming, Kepler needed to concentrate on a small subset. Years earlier, he had worked on the Mars data with Tycho, and he was familiar with its nuances. He decided to begin his inquiries by investigating the orbit of Mars. Kepler was immediately faced with a problem which dated to the origins of astronomy in the ancient world. The Greeks had made two assumptions about the orbit of celestial bodies. The first is that they move in perfect circles, and the second is that they travel at uniform speed. These postulates derive from Aristotle, and while they may have not been original to him, they were accepted largely on his authority. Yet, these assumptions caused issues for later astronomers. For example, if you viewed the planet's orbits, they don't seem to be moving regularly. Mars in particular was one of the most wayward. Viewed from the Earth, Mars doesn't seem to be travelling at a uniform speed. At some points in its orbit, it moves faster, while at others, it's slower. The evidence of the eyes betrayed the assumption of uniform motion. Ptolemy had been aware of the problem and introduced two tools to try and save uniform circular motion. The first of these was the eccentric. The eccentric model has the planets orbiting in a circle around a stationary Earth, but with the Earth offset from the centre. The effect of this is that when the planets are closer to Earth, they seem to be moving faster, and when they are further away, they seem to be moving slower. You can understand this if you picture a speeding car. If it passes right in front of you, it seems to be moving much faster than if you're viewing it from a kilometre away. Unfortunately, the eccentric alone was not enough to solve the issue. Ptolemy found that to get the models to fit the observations, he needed to introduce an additional device known as the equant. In the equant model, the planet no longer moves at uniform speed around the centre. Instead, it moves at a constant rate around another point off to the side called the equant. Ptolemy placed the equant on the opposite side to the eccentric, so they were both some distance from the centre. With the eccentric and equant in place, Ptolemy could make pretty good predictions for the positions of the planets. The equant, though, would become the most controversial part of Ptolemy's astronomy. The planets no longer moved uniformly around the middle. This was clearly not in the spirit of Aristotle's assumptions. Later astronomers concluded that Ptolemy had cheated and sought solutions. In the Islamic world, Al-Shatir demonstrated that the equant could be eliminated by introducing additional epicycles. Epicycles are the small orbits which are carried around on larger orbits called deferents. In the West, Copernicus came to the same conclusion, except he also placed the Earth in motion. Al-Shatir was mostly unknown in Europe, so Copernicus was credited with the elimination of the equant. Kepler began to work on Mars's orbit with full knowledge of Ptolemy and Copernicus's models, but approached them with a fresh outlook. Kepler was a committed heliocentrist. He took it for granted that Mars orbited the Sun. From Ptolemy, he kept the eccentric orbit, but in reverse, so the Sun was slightly off-centre as Mars moved around it. But Kepler knew this wouldn't be enough to reproduce the observations, so he reintroduced the equant. This was a bold decision. In the 16th century, eliminating the equant was viewed as Copernicus's greatest success. For Kepler, though, there was no place for the epicycles introduced by Copernicus's theory. He didn't see why planets should orbit around an empty point in space. Instead, he thought everything should orbit the Sun, which provided the force to keep things moving. In his view, if the planets seemed to be speeding up and slowing down, it's because they really were. Fundamentally, Kepler was discarding Aristotle's assumption of uniform motion. His early model for Mars's orbit looked like this. Mars moved around the Sun in a circle. The orbit was eccentric, with the Sun at some distance away from the centre. On the other side, he placed the equant, which was the point around which Mars moved at a constant speed. But Kepler wanted to further refine the model. Ptolemy had placed the eccentric and equant on each side of the centre at an equal distance. This is called a bisected eccentricity. To Kepler, though, this placement was completely arbitrary. Ptolemy only kept it because it worked well enough for the observations he had. Kepler decided to try to improve the model by refining the placement of the equant and eccentric. This was possible now because he had access to Tycho's superior data. Nevertheless, this was a challenging task. The mathematics of the time wasn't suited to tackling such a problem. So, Kepler invented his own procedure. He used an iterative method where very gradually he fine-tuned the positions of the eccentric and equant. Kepler hated this work. He wrote, "If you're weary of this tedious procedure, take pity on me, who carried out at least 70 trials." The calculations were extremely laborious. He began to speak of his investigation as his war with Mars. Over the next 2 years, he would face many similar struggles. Each new method of analysing the orbit was another assault on the planet, and each time the planet inevitably fought back. In this battle, however, he achieved a small victory. He managed to optimise his model so that it could predict Mars's position to within 2 minutes of a degree of arc. To compare, Ptolemy's model was, at best, about 10 minutes of arc. Kepler could not have created a better model. The accuracy was equivalent to the resolution of Tycho's data. At this point, Kepler could have been satisfied with his achievement and called it a day. He had reached the goal of contemporary astronomers who wanted to predict Mars's position. But, as he would later write, just because a model did a good job of calculating, it didn't necessarily reflect reality. He wanted his model to be consistent. Kepler could predict one aspect of a planet's position. When pre-modern astronomers talked about a planet's position, they usually meant how far it had moved around in its orbit, or in other words, what angle the planet had passed through as it moves around the circle. This is called the planet's longitude. But this doesn't capture everything about a planet's position. In an eccentric orbit, the distance between the planet and the Sun also varied. Kepler wondered, could his theory also predict the planet's distance from the Sun? Using some clever trigonometry, he tested his model and found that the distance to Mars disagreed with the observations. The errors were as much as 40% in some cases. He looked again at the placement of the equant and eccentric in his model. If he undid his work and put the equant and eccentric back to where Ptolemy had them, the distances were correct. Unfortunately, when he did this, the errors in longitude were greater, around 8 minutes of arc. Prior to Kepler, this would have been considered acceptable. For earlier astronomers, an error of 8 minutes would have been hidden by the resolution of the observations. But Kepler knew Tycho's data was superior and wasn't willing to put up with this degree of accuracy. He wrote that Tycho was the most diligent observer and trusted that the 8-minute error was real. In the war with Mars, Mars had struck back with a devastating blow. He named this model the vicarious hypothesis and discarded it as a working theory. Kepler believed that any model must be physically consistent. To him, models were not just mathematical tools. Instead, they should reflect the world as it really is. Ptolemy and Copernicus would have been happy to have one method for calculating longitude and another for distance. Kepler wasn't. For him, the planets orbited the Sun, and that was that. Any model worth a damn must predict exactly where the planet was at a given time. But as he was working on this, he was suddenly interrupted. In October 1602, Franz Tengnagel, Tycho's old assistant, returned to Prague. He was accompanied by Tycho's daughter Elizabeth, whom they had married the previous summer. Since then, they had been away, visiting the Netherlands, and in their absence, missed Tycho's death and funeral. On returning, Tengnagel found that no one had been dealing with Tycho's affairs. There were promises from the Emperor for Tycho's instruments, but no payments had been made from the royal treasury. He visited Kepler and asked him what progress he had made in completing the new astronomical tables. Kepler had made no headway, having spent the year battling with Mars's orbit. This infuriated Tengnagel, who took it upon himself to act on behalf of the Brahe family. Tengnagel, unlike Kepler, was a nobleman. At court, he used his influence to have responsibility for compiling the new tables transferred to himself. The row escalated and brought Kepler to the attention of the Emperor. At court, Tengnagel had loudly criticised Kepler, calling him slothful. This led to Rudolf summoning Kepler and asking him what he had been working on. Grasping for a project he thought he could finish quickly, Kepler promised the Emperor 2 new books, one on the optical part of astronomy, and another with his commentaries on Mars. Kepler realized he would have to start working on these immediately. Most damaging to Kepler, though, Tengnagel demanded the return of all of Tycho's observations. Initially, Kepler declined. He needed them, and besides, Tengnagel was unlikely to make use of them himself. In response, Tengnagel brought a lawsuit against Kepler. Kepler was angry and disappointed. In desperation, he handed back most of the observations, but secretly kept the Mars data. Quietly, Kepler continued to work on the orbit of Mars for the next year. He began by reflecting on his failure. The vicarious hypothesis had had a great success in predicting planetary longitudes, but this didn't satisfy Kepler. He wanted to know the true path of the orbit. Kepler realized he had pushed the traditional framework as far as it would go. Now he would have to try something radically new. To make progress, he returned to his most fundamental physical idea, that the Sun was responsible for the motion of the planets. He had first formulated this while writing Mysterium Cosmographicum several years before. Kepler believed that the Sun was analogous to God the Father. The Sun provided light and heat, and so it made sense that it was also at the centre, controlling the planet's motion. However, there was also an empirical element to Kepler's thought. From Copernicus, he learned that the planets further from the Sun seemed to be travelling more slowly than those closer to the Sun. He conjectured that this was because of a force which emanated from the Sun and influenced the motion of the planets. As a planet moved closer, it sped up, because the force acting on it had increased. This idea underpinned his conception of the equant mechanism. Kepler made his new assault on Mars by considering exactly how the speed of the planet varied with distance. He suggested that a planet's speed was inversely proportional to distance. Kepler called this his distance law and realized he might be able to use it to his advantage. If he knew how far Mars was from the Sun, he could calculate its speed and work out where it would move next. Kepler wanted to use this distance law to map the orbit of Mars. The problem was that the planet's distance changed continuously, as did the speed. Kepler didn't have the mathematical tools to deal with continuous change. The best he could do was break up the Mars orbit into 360 individual segments, each equivalent to about 1 degree. For each part, he could calculate the distance to the planet, assume the distance was constant, and calculate the average speed in this small segment. But in practice, this didn't help much. To make this calculation even once was complex and time-consuming. Around the whole circle, it was impossible. The solution for Kepler was to switch his thinking from considering distances to considering areas. Looking again at his 360 segments, he realized that the area of each was proportional to the time taken to move through the segment. This was because in the parts where the planet was further, it was also travelling slower, and in the parts where it was closer, it was travelling faster. In other words, the same area was always swept out by Mars in the same period of time. Kepler called this his area law, but today it's known as the second law of planetary motion. This, though, was just the start for Kepler. His aim was to use the area law to map Mars's position. He found the expected positions or longitudes of Mars as it moved around its orbit. Results were disappointing. The positions differed by as much as 10 arc minutes to the real positions. He checked his calculations for potential errors, but found they were all too small to account for the difference. At this point, Kepler could have abandoned his area law. Instead, he considered another possibility. What if the distances were wrong? It seemed that Mars was running too slowly at the furthest point and too quickly at the nearest point. Or in other words, Mars was really further away than he expected at some points and even closer than he expected at others. If this was true, it implied that the orbit wasn't a perfect circle. Kepler checked his calculations, and they seemed watertight. He made the leap and ditched the circular orbit. Kepler had already advocated for heliocentrism and non-uniform motion. Now he was abandoning circular motion, the last assumption of ancient astronomy. The next step was to find out what shape the orbit actually was. Unfortunately, around this time, Tengnagel realized that the Mars data was missing and forced Kepler to return it. Without the observations, Kepler had to stop. This was frustrating, but he had no choice. He had also assured the Emperor a publication, and he needed to start work on it. As he didn't feel he had finished with Mars, he turned his attention instead to his optical work. He started to write a book called Astronomia Pars Optica, or the optical part of astronomy. The work was intended as a study on how optics affects astronomy. While Kepler treated the book as something like a side project, he reached some new and important results. Prior to Kepler, most people studying optical science had concentrated on describing light in terms of visual rays. This was important, but it's not the only relevant feature in understanding light. Kepler investigated the intensity or brightness of light and how it varied. He argued that intensity decreases with the square of the distance. His argument was based on geometry. Imagine a candle. Light will be emitted in all directions and form a sphere which spreads out from the centre. If you double the distance from the centre, the sphere will be 4 times greater. The same amount of light then will be spread over 4 times the area, meaning the intensity or brightness of the light is 4 times less. This was a novel argument. Kepler's work pioneered the mathematical treatment of light and foreshadowed the development of physics over the next century. And this wasn't the only new discovery described in the book. The purpose of Pars Optica was to explore the effect of optics on astronomical observations. Kepler inherited from prior astronomers an interest in refraction. Since Ptolemy, it had been understood that astronomical observations would be subject to refraction as light entered the atmosphere. The problem was trying to quantify how much refraction actually occurred. Tycho had collected a huge number of observations trying to measure refraction, but his conclusions had been hindered by his faulty belief that refraction depended on the type of light. Kepler, unfortunately, inherited this misleading assumption and used Tycho's data to compile tables of refraction for the Moon, Sun and stars. His attempts were also hindered as he lacked a correct understanding of the law of refraction. He knew that the relationship between the angles of incident and refraction was non-linear, but he didn't have the experimental data to flesh out the full law. Instead, he used his understanding of refraction to answer another ancient question. That is, how do we see? Kepler had been troubled by this question for a few years. It began 2 years prior with his investigation of the pinhole camera. From Tycho, he learned that the sizes of the Sun and Moon aren't projected accurately when viewed through the aperture of a pinhole camera. Kepler's explanation was that the pinhole causes the objects to blur, which affects the measured diameter. From this, he came to the broader realization that all astronomical phenomena have some dependence on the optical equipment through which they're viewed. He worried that the eye, which also had an aperture, might be prone to the same errors. Kepler began his investigation by examining earlier theories of vision. He was familiar with the work of Al-Haytham, who thought that the lens of the eye was the seat of vision. That is, the lens detects the light and sends the image to the brain. But Kepler realized this was wrong. His breakthrough came from reconsidering the pinhole camera. In the pinhole camera, light passes through an aperture, which causes blurring of the light. You can get a sharper image with a narrower aperture, but this comes at the cost of less light passing through. The eye is similar to the pinhole camera in that light also passes through an aperture. However, we know the eye forms a much clearer image than the pinhole camera. If our eyes are functioning properly, there's no blurring at all. Kepler realized this is because of the lens. When light enters the eye, the rays refract at the lens. Because of the lens, light rays don't spread out, but instead converge down to a point on the retina. This keeps the image sharp, despite the finite size of the aperture. Al-Haytham had not appreciated the real purpose of the lens. He thought that it detected light. In reality, the lens is responsible for bending light and creating a sharp image. For Kepler, it's the retina at the back of the eye that becomes the seat of vision. This was a remarkable discovery. In his spare time, Kepler had solved a problem that was almost 2,000 years old. When Astronomy Pars Optica was published in September 1604, it received only a modest amount of attention. As with most of Kepler's books, it was written in a style of dense mathematical arguments that were difficult for most readers to follow. Only later was it widely read by specialists, and it did eventually have a large impact on the development of optical science through the 17th century. As he was finishing Pars Optica, a miraculous event turned his attention back to astronomy. On the 11th of October, a court official awoke Kepler at dawn. The man was in a state of agitation and blabbered excitedly. After he had calmed down, Kepler learned the man was claiming to have seen a new star appear in the night sky. Unfortunately, when Kepler tried to check that evening, the skies were overcast and remained so for the next 6 nights. On the 7th night, just as he was beginning to doubt the official's story, Kepler saw the star for himself. The star appeared near the conjunction of Saturn and Jupiter and was as bright as the planets themselves. Because of its appearance near the conjunction, popular speculation began that the planets had ignited the nova. Worse still, it appeared in a region of the zodiac associated with fire, a sign thought to foretell danger and chaos. The population was nervous, so the emperor asked the imperial mathematician for his opinion. Kepler was doubtful that the appearance of the star could be linked to events on Earth. He took his time to reassure the populace. Although he didn't believe that the conjunction had ignited the nova, neither did he believe that it was a coincidence. Kepler instead took the appearance of the nova as a sign from God. He suggested that the populace should examine their sins and repent. As a deeply religious man, he doubtless thought they should be doing that anyway. For Kepler, the appearance of the new star coincided with the reappearance of Tegnagel. Tegnagel had been trying to complete the planetary tables himself, but he had made little progress. He was forced to concede that he couldn't do it alone. An agreement was struck where the data would be sent back to Kepler, who in return would seek Tegnagel's approval before any publications. Not entirely trusting Kepler, Tegnagel insisted that these terms should be drawn up into a formal contract. Naturally, Kepler didn't immediately get back to work on the tables. Instead, he returned to the subject of Mars's orbit. He had already decided that the orbit was not a circle, but determining its true shape would be another monumental task. Kepler resumed the war with Mars, spending night and day performing unending calculations. Corresponding with Longomontanus, Kepler said that he had tried to fit 20 different types of ovals. Eventually, as an approximation, he settled on an ellipse, realizing this would greatly simplify calculations. As it turns out, this approximation fit remarkably well. After all of his effort, he was reluctant to accept that the simplest answer was also the correct one. But the data fit. He discovered it worked particularly well when he placed the Sun at one of the foci of the ellipse. This configuration became known as the first law of planetary motion. Kepler now had a working theory which described planetary motion exactly. However, he still felt obliged to try and explain why the planets moved as they did. Previously, Aristotle's assumptions of uniform circular motion had been the foundation. Some later astronomers built on this idea, stating that the planets were carried along by rotating crystalline spheres. Tycho's observations of the Great Comet had done away with this idea by showing that the comet's pass would have torn through these spheres. Kepler looked for an alternative which could explain his non-uniform elliptical orbits. He returned to the idea that a force from the Sun was moving the planets along, but the question was, what kind of force? Kepler decided that the force must travel through space and keep the planets in their orbit. From a natural philosophy perspective, this was controversial. The ancient Greeks had largely rejected the idea of action at a distance. But times were changing. A few years earlier, an Englishman, William Gilbert, had published his treatise on magnetism. Gilbert had argued that magnetic forces acted at a distance due to a sphere of virtue which surrounded the magnet. What's more, Gilbert had also demonstrated that the Earth itself was magnetic. He speculated that the magnetic force was acting on the planets, keeping them in orbit. The issue was that this force, according to Kepler, was required to keep the planets moving along in their orbits. He wondered how this was possible, as surely the force moved out radially from the Sun, whereas the planets moved perpendicular to this force. His solution was to suggest that the Sun drags along the planets as it rotates around. The full theory of the magnetic Earth was complex and convoluted, and Kepler appreciated it was highly speculative. Nevertheless, it was an important step. Kepler had based his astronomy not on arbitrary postulates, but on physical principles. Kepler began to collect his conclusions. Although he had originally intended his work as a commentary on the orbit of Mars, he realized that his conclusions were much broader. The laws he had discovered for Mars's orbit could just as readily be applied to all of the other planets, including Earth. He titled his new work Astronomia Nova, or the New Astronomy. By the middle of 1605, Kepler was finally ready to publish. The manuscript ran to over 300 pages, and its structure was entirely novel. In similar works, such as Ptolemy's Almagest or Copernicus's On the Revolutions, the authors had started with a set of axioms, and proceeded to formulate their theories from these basic principles. Kepler consciously took another approach. He included his entire process of discovery, including every misstep and dead end. This meant the work would be complex to read, but Kepler felt he needed to justify how he had arrived at his ideas. The book was ready to print, but because of the agreement with Tengnagel, it would have to be checked first. Tengnagel was not pleased. Clearly the work was arguing for a Copernican rather than tychonic arrangement. In Kepler's defense, he had gone to lengths to honor his word to Tycho. In the new astronomy, he had made extraordinary efforts to develop and investigate Tycho's geoheliocentric system. The problem was, to get it to fit with the data would have been extremely complex, whereas his own heliocentric system was simple and elegant. For Kepler, this truth stood above his loyalty to Tycho. Tegnagel, by contrast, prioritized Tycho's legacy, and with the contract struck years before, he had the power to prevent publication entirely. But Kepler would not be dissuaded. In a typical display of boldness, he applied for the printing costs from the emperor anyway. In addition, he asked the emperor for an imperial order to ensure the work would be published. If granted, this would be leverage Kepler could use against Tegnagel. The argument dragged on until 1607, when the two parties entered into a formal negotiation. Fortunately for Kepler, Tegnagel was preoccupied at the royal court. He didn't have the time, and also perhaps the ability, to wade through hundreds of pages of dense astronomical argument. The two men came to an agreement where the main part of the book would not be changed, but a preface, written by Tegnagel, would be appended. The preface ultimately is a short, incoherent ramble. It's doubtful that the preface did much to detract from Kepler's work. There were further problems in the printing of Astronomia Nova. The emperor had granted funds of 400 florins for printing. As usual, though, the treasury had been failing to provide Kepler his salary, and the delay caused by the spat with Tegnagel meant that by 1607 the book had still not gone to print. In the meantime, Kepler had been forced to spend some of the money on household expenses. Kepler had the book printed with the money he had, and promised the rest later. This plan was complicated by the emperor's demand that the book should not go on general sale. He wanted to distribute the book personally. Unsurprisingly, when the book was finally printed, no money was forthcoming, and Kepler was forced to sell the first edition back to the printers. It wasn't until around 1610 that the book became generally available, and it was decades before its conclusions were felt. Nevertheless, Kepler could be satisfied. His astronomy was always motivated less by external praise and more by his desire to search for truth. Kepler believed that the universe was created in God's image, its harmony reflecting his perfection. His work in Astronomia Nova had answered all of the old questions, and Kepler may have been wondering what was left. However, this was an exciting period in the history of science. It would not be long before new questions emerged. One March morning, a carriage drew up outside Kepler's house. Inside was his friend and distant relation, the imperial councillor Wacker von Wachenfels. Wacker stepped down from the carriage onto the cobbled streets and shouted up to Kepler, Johannes, have you heard the news?" Kepler peered out a window, down to his companion, and wondered what the fuss was about. "What news?" replied Kepler. "I bring word from Italy, Johannes, from Galileo. He's discovered 4 new planets."